typical exam style question. Here is a typical exam style question. Okay. It relies on you having a good understanding of resolving forces in different directions. Okay. Understanding the difference between line of action, direction of motion. Okay. Resolving forces so that you can find the forces acting either in the direction of motion or perpendicular to the direction of motion. So just on the sideline here, perpendicular to the direction of motion. So in other words, if that's the direction of motion, any force that is acting 90 degrees to that force, there's two things that you can tell me without a doubt are not going to happen. There's going to be no acceleration perpendicular to the force, and there's going to be no motion. So therefore, what are we just talking about now? Work. So there's no work. So that's important to remember those things. There is no acceleration. Those forces are in equilibrium. That's why that object's not moving in that direction. Okay? So if we consider this slope here, we have this box being pushed up the slope. Okay? What would you say it were is its direction of motion? It's not in the book, so you can look there all you want. I want you to think about it.
It would be down.
No. It's being pushed up the hill. So what if you had to point an arrow in the direction that box is moving? Would you say it's moving in this direction, or in the direction of the slope? Yeah, in the direction of the slope. Well, we can't say for a fact that it's doing that, but I think the question tells us that it's doing that, so we can assume that that's the direction of motion. Sometimes we make an assumption and we'll find out afterwards we've made the wrong assumption. Okay? But we can assume for now this is the direction of motion. Okay? That means any force acting in this direction, we don't care about for the purposes of this question, because this question is going to ask us a whole bunch of work questions. If something's not moving in that direction, it can't be working in that direction. Okay, so there's no work being done. Okay, the first thing they want us to do is find the work done against friction. Okay, so work is being done against something. Think about against gravity, you're going to get a negative force. Okay, so it's working in the opposite direction that the object is moving. In other words, it's working to prevent movement. Okay? So let's go A, work equals force times distance. What is the force of friction? Did we have to calculate it, or was it given to us? It's given to us as 2 newtons. So the force is acting in or against direction of motion. Well, friction always acts against. So it's minus 2 newtons times, what's the distance that the box moved? 3 meters up the slope. And so we're going to get 6. You're lazy. Why must I write M when I can just write joule? Why am I not putting minus sign there? No, the reason we're not writing negative there is because work is a scalar. Just like speed, it doesn't have a negative. But what can I write here? 6 joules against friction.
We know friction.
Okay. Okay, let's go to Mr. B. Okay, work done against gravity. And what work is being done against gravity? Now,
Yeah, it's just the same, then -2 and
okay, well, here's gravity here. Here's gravity here. Is it pointing in the direction of motion? So that's a bit of a problem, isn't it? Okay. Because it's at an angle to the direction of motion, there are two components to that weight force. Because we are at an angle, okay, one of those forces is in that direction, and the other force is acting in that direction. Right? Those are its two component forces. Okay. One of those forces has no impact on the work being done. Which one is that? Zara? Would you say it's this force or this force? This one, yeah. Well, the very easy way to prove that is to say, well, you see this force here, which direction is it pointing? Perpendicular to the direction of motion. And what do you know about perpendicular forces to motion? No acceleration, no work. So I don't care about this force here. It's not doing any force, any work in the direction of motion. So the only one I care about is this guy here. Right? What is that side in the triangle? So we can redraw this force down over here, right? With some simple manipulation, if this is 30 degrees, this must be 60 degrees. Therefore, this angle must also be 30 degrees. That force, is it opposite or adjacent to 30 degrees? It's opposite. It's all the way on that side. So it's going to be sine. Okay? So that force, right, is, well, you could write this cos theta nonsense. Actually, you can't because we're not considering the force at that angle. So that's why you have to be careful about memorizing formulas like this. Because now I say, when you're calculating work, you always use cos. Okay? You have to consider every problem individually. So always draw your diagram and always consider if it is the adjacent or the opposite side. Let's check that out. Let's first calculate the force so that we don't make mistakes. That is going to be, what's the size of the weight force? The weight is 5 kilograms, so it's 50, yeah? 50 sine 30. Oh, sine 30 is a nice one. That's just. And so what's the force? What is the horizontal force, component force of the weight? 25 newtons. Right, now we can calculate work. 25 times how far the bottom is? 3 meters. So that is 75 newtons, I believe. Okay. Now, I'm being very naughty. Okay. Very naughty. Teaching you wrong. In which direction is this 25 newtons acting? In the opposite direction. So it's actually minus 25 times 3. That gives me 75 joules. I'm not going to write the minus sign. I'm going to write against gravity. Again, I know it makes me angry too that we can't just call it a vector. It should just be a vector, right? But because work, when we look at, I believe, potential and kinetic energy, it will make more sense why work is not negative. Right? Because energy is a scalar quantity as well. All right, let's have a look at C. Find the work done by the push force. Okay, so Toya, where's the push force? I'll even zoom in for you over there. You see the push force, right? It's this guy here, isn't it? It's at an angle. So can I just consider it going up the direction of motion? No, unfortunately, I have to also resolve it into its two different components. Okay, So while we've got it zoomed in here, let's just do that, okay? This force is going to have two forces. It's actually going to have a force going up like that and a little force going up like this. Okay? Well, I know that this is 10 degrees because they told me that. The force I'm interested in is that guy there. Because this guy, well, he's going perpendicular, so I don't care about it. Okay? What side of the triangle is that in relation to the 10 degrees that I have? It's adjacent. Okay? So that's the adjacent side. So if I want to calculate the size of that force, that's going to be equal to 30 newtons times by cos 10 degrees. That's for the force. Right, now we want to calculate the work done. Work is equal to force times distance. What's the distance that it traveled? 3 meters. Is this force positive or negative? This force is positive because it's pushing in the direction we want to go. So we're going to have 30 times 3, so we'll have 90 cos 10 degrees. Joules. Why am I not converting that into any numbers yet? Because I don't know what cos 10 is. I'll wait for Zara to get a calculator out just now. Not yet, not yet, not yet. In a textbook, they've already written out. And if you had technically done this question, you would go 3 significant things. Okay? Okay, question D says find the work done by the normal reaction. Ugh. What's the normal reaction? We use another word for it. We've used another word, the normal contact force. Okay? So where is the normal contact force in that diagram? Is it labeled? It is actually labeled. Remember, normal contact force acts perpendicular to the surface. Okay, so here is my normal contact force. What can you tell me about that force? It is direction of motion. So, is there any acceleration? No. Is there any work done? No. So, what work is being done by the normal contact force?
Well, is it perpendicular to the
surface?
motion?
So,
yeah, I know it's to the surface, but you said also perpendicular to the direction of motion.
So, because this box happens to be moving at exactly the same angle as the surface, its direction of motion is the surface. Okay?
Okay, so not like any technicalities, like
we're not considering that maybe the box is actually not going perfectly up the slope, but maybe at sort of an angle. Okay, because that would just be painful and not nice. So to make life easier, we're just saying yes, it's going at exactly the same angle as the surface. Or think about a car, actually, a car driving up the slope. Its direction of motion will always be the direction of the slope, unless you're again maybe being naughty and a hooligan and driving really fast to generate some kind of lift or something like that. Okay? However, in our situation, that normal contact force is perpendicular to the surface, which happens to be perpendicular to the direction of motion. And so, what is the work done by the normal contact force? Nothing. Okay. So you don't want to go now work it out because you could work it out. And then multiply it by the distance. But think about it. What distance has that thing moved perpendicular? It hasn't moved in that direction. It moved in this direction. So its work is in that direction. Okay, finally we get to the crux. The finale. Find the work done on the box by all 4 forces. Okay, so let's go back and look at all 4 forces. Okay, we had the force against friction. We had the force against gravity. We had the pushing force and we had the normal contact force. And we want to work out the total work done. Well, one of those we can already tick off and get rid of. Oh, which one is that? No, there was no. Okay. So now we can consider all the other forces. So let's say the total work done. Now this is where you're going to hate me. I'm going to say to you, work isn't a vector, but you still have to consider the direction it points in. Okay. So the work done by friction was 6 joules. Okay, but it was against, but it was not in the direction of motion. So what's it going to be? -6, hey? Okay. The weight component, the work done against gravity, that was down the slope. So it was -25 newtons. Sorry, it was -75 newtons. Thank you, Zara. I'm looking at the force and not the work done. Okay. And now we can consider the work of the pushing force, okay, which we calculated as 90 cos 10. So Dora, you can do the magic for me. 7.632, etc. So if we were rounding to 3, remember guys, not 3 decimal places, it's 3 significant figures. So 3 significant figures means you count 1, 2, 3, and the buck stops there. So you would 7.63. Okay. Now, let's say the question asked us to calculate the total work done by all the forces, right? But they haven't asked us to find all the component forces first. So you see how this question staged you. You got the work for this force, work for that force, work for that force, and eventually we can find out the total work done for all the forces. If you were doing this and the only question asked of you was find the total work done by all 4 forces, what could you have done? I want you to go back and I want you to consider when we were working with acceleration. If I asked you to calculate the acceleration for something, you had to do something first. Remember, acceleration can only happen in one direction, right? And that direction is the direction of motion. You accelerate in the direction that you are traveling, or decelerate for that matter, okay? What do we call that direction in terms of forces? It's actually the F in Newton's second law. And what is that F? That is the, I always tell you, that's not force, that is net force. What's net force? Yeah, we take all the forces, we consider them together, the resultant force, okay? So, in this example, if we had considered the resultant force of all those forces, it would have given you some force acting in that direction. And how would you have done that? Well, you would have resolved vertically. Vertically, we have to be in equilibrium because it's perpendicular to the motion. So we would have had to resolve horizontal. And how would you have done that? Well, you would have had to split the forces up into the 2 different components. You would have taken all the forces in that direction as positive, all the forces against direction as negative. You would have found a single force. And actually, we can go back and we can do that. Right? Let's quickly go and have a look at that. Right? We can do it over here. Right, what's the force, the pushing force up the hill? It was 30 cos 10, because the only thing we're interested in is that force there. That's in the direction of motion. Okay. What was the friction force? -2, eh? What was the weight force? Pulling the car back down the hill, or box down the hill? That was 50 sine 30. Okay. So what was my net force? You'll have to quickly do it on your calculator, Sarah. 2.54. That is the net force in newtons. Okay, and how far did the box travel? 3 meters. What do you get? Well, obviously, it's the same. So total work done, if you're very lazy and if you don't have to ask or work through all the different steps, is the net force times distance. Cool. You can write those down. Like you have the whole weekend to do that.